This video presentation is brought to you by the Pro Mathematics Academy.
Welcome to another video presentation brought to you by the Pro Mathematics Academy. In this video, we'll be looking at the 2015 Unit 2 CAPE exam, question number 1. So without further ado, we jump right in. And here we are given three complex numbers, z1 equal 1 plus 7 minus 4 square root 3i, z2 equals square root of 3 plus 3i, and z3 equals minus 2 plus 2i. We're asked to express the quotient z3 divided by z2 in the form x plus iy. Okay, so we first take z3 divided by z2 equals minus 2 plus 2i divided by the square root of 3 plus 3i. And we want to multiply throughout by the conjugate of the denominator, right? So whenever we have a ratio of two complex numbers, we want to multiply throughout by the conjugate of the denominator. Recall that if z is equal to a plus bi, then z star, the conjugate, is a minus bi. All right, so that when we multiply a minus bi times a plus bi, we end up with a squared plus b squared. So taking z3 divided by z2 equal minus 2 plus 2i divided by the square root of 3 plus 3i times square root of 3 minus 3i divided by the square root of 3 minus 3i, we can now multiply the numerators with numerators and denominator with denominator. We end up with minus 2 plus 2i in bracket times square root of 3 plus 3i in bracket divided by the square root of 3 squared plus 3 squared, which is equal to minus 2 square root 3 plus 6i plus 2 square root 3 minus 6i squared, all divided by 12, which is the same as minus 2 square root 3 plus 6 divided by 12 plus 6 plus 2 square root 3 divided by 12 times I. And that is our answer for part 1. Now we move on to part 2. Given that the argument of W is the argument of Z3 minus the sum of the argument of Z1 and Z2, where Z1's modulus is equal to 1 and the argument of Z1 is equal to pi divided by 12. Rewrite W equals Z3 divided by Z1 times Z2 in the form of R times e to the I theta, where that is the exponential polar form for our complex number, where R is equal to the modulus of W and theta is equal to the argument of W. So we take W equals Z3 divided by Z1 times Z2 equals R3 e to the I times theta 3 divided by R2 e to the I times theta 2 times R1 e to the I times theta 1. And that simplifies down to R3 divided by R2 times R1 times e raised to the I theta 3 minus theta 1 plus theta 2 times I. This can be simplified further based on the fact that modulus of Z1 is equal to 1. So this means that W is actually equal to R3 divided by R2 times e to the I times theta 3 minus I times theta 2 minus I times theta 1. And if we separate our I times theta 1, then we can write this as R3 divided by R2 times e to the I multiplied by theta 3 minus theta 2 times e to the minus I times theta 1. So if we look closely, we'll realize that this expression right here is the complex number for Z3 divided by Z2, which we previously solved for. Right? So we know Z3 divided by Z2 is equal to 6 minus 2 square root 3 divided by 12 plus 6 plus 2 square root 3 divided by 12 times I. We can convert this complex number into its polar form, right? And to convert it into its polar form, we need to know the modulus of the complex number and its argument. So let's go for the modulus first. R is equal to the modulus of Z3 divided by Z2, which is equal to the square root of 6 minus 2 square root 3 divided by 12 all squared plus 6 plus 2 square root 3 divided by 12 all squared. So after taking the square root of that, we end up with the square root of 2 divided by 3. Then we have to move on to find the argument. So to find the argument, theta of a complex number z equal a plus bi, we use the formula theta equals tan inverse of b divided by a. but we can check this on our organ diagram to confirm. Right? So let's draw up our organ diagram here. We put in our real z-axis for our x-axis, and we put in our imaginary z-axis for our y-axis. Putting in A, which is our real part, and then putting in B, we can write in theta right there. So it is important to define theta at this time. We say that theta is the angle formed between the positive real z-axis and the line segment connecting the origin O with the complex number z. And there we have it. We can now recognize that theta is equal to tan inverse of the b component divided by the a component. Here our b component is 6 plus 2 square root 3 divided by 12, and our a component is 6 minus 2 square root of 3 divided by 12. Plugging that in our calculator, we end up with 1.30899693 on my calculator. We then divide by pi, which gives us 0.416666 pi, which means that we can convert that repeating decimal into 5 divided by 12 pi. Moving right along, we go back to W. So now we realize that W is equal to Z3 divided by Z2 times e to the minus I times pi over 12. And we should recall that the question gave us this value for theta 1, which is equal to pi over 12. And it also said Z, the modulus of Z, is equal to 1. So this then implies that we can plug in our result that we just calculated. W is now equal to the square root of 2 divided by 3 times e to the I times 5 over 12 pi times e to the minus I times pi over 12. Those two exponents are subtracted and we end up with W equals square root of 3. W equals the square root of 2 divided by 3 times e to the I 4 pi divided by 12, which simplifies down to the square root of 2 divided by 3 e to the I times pi over 3. Thus, the argument of W turns out to be pi over 3. Part B of question number 1. We're given a complex number V equals x plus iy, right, is such that v squared is equal to 2 plus I. Show that x squared is equal to 2 plus the square root of 5 divided by 2. Note that this is our end result. Now, if v is equal to x plus iy, this means that v squared is equal to x plus iy all squared. Expanding that gives us v squared is equal to x squared plus 2xy times I plus iy all squared, which is equal to x squared plus 2xy times I plus I squared times y squared. But we recall that I squared is equal to -1. This then means that x squared plus 2xy I minus y squared equals x squared minus y squared plus 2xy times I. So now we look back at our question and we realize that the question said v squared is equal to 2 plus I. So this means that x squared minus y squared is equal to 2 and 2xy is equal to 1 by equating real with real and imaginary with imaginary. So taking our second equation there and transposing for y, we end up with y equals 1 divided by 2x. Subbing that into our first equation, we end up with x squared minus 1 divided by 2x all squared equals 2. This then means we have x squared minus 1 divided by 4x squared equals 2, which means we can now multiply through by 4x squared. This then gives us 4x raised to the 4th power minus 1 equals 8x squared after multiplying throughout. We then realize that we have 4x to the 4 minus 8x squared minus 1 equals 0 after bringing everything to the left-hand side. And then we realize this equation is a quadratic in x squared, which means we can use the quadratic formula. X equals minus b plus or minus the square root of b squared minus 4ac all divided by 2a. So here we have x squared equals 8 plus or minus the square root of 8 squared minus 4 times -1 all divided by 2 times 4. So we have to use the quadratic formula there, substituting a for 4. B for -8, and C for -1, which then allows us to simplify further. So we now have 8 plus or minus the square root of 64 plus 16 all divided by 8, which gives us 8 plus or minus 4 times the square root of 5 divided by 8, which then we can cancel 4 out of all of those terms, which then gives us 2 plus or minus the square root of 5 divided by 2, QED. That is our result which we were trying to prove. Moving right along to part C, which asks us to find the derivative of this parametric equation. So, we're given a function f is defined by the parametric equations x equal e to the minus t divided by the square root of 1 minus t squared, and y is equal to sine inverse t for t on the interval -1 to 0.5, not inclusive of -1, inclusive of 0.5. So, we're to show that dy dx is equal to e to the t times 1 minus t squared all divided by t squared plus t minus 1. So, for parametric equations, dy dx is equal to dy dt times dt dx. So, we have to find them separately. This is an important note, and then multiply them. So, we have x equals e to the minus t divided by the square root of 1 minus t squared. So, dx dt is equal to the derivative of e to the negative t divided by the square root of 1 minus t squared. Here, we have to recognize that we must use the quotient rule of differentiation. Applying the quotient rule of differentiation gives us the denominator squared, which is the square root of 1 minus t squared all squared, gives us 1 minus t squared. And then we have the square root of 1 minus t squared times e to the negative t times -1 minus the derivative of our denominator, which is 1 divided by 2 times the square root of 1 minus t squared times -2t. And then we multiply by our original function, u, which would have been our numerator, which is e to the minus t. This then gives us e to the minus t times, in bracket, the negative of the square root of 1 minus t squared plus t divided by the square root of 1 minus t squared, all divided by 1 minus t squared. We're just simplifying here. This gives us e to the minus t times the negative of 1 minus t squared plus t, all divided by square root of 1 minus t squared, tidying up our numerator there, which leaves us with 1 minus t squared still as our denominator, which then simplifies further to e to the minus t times the negative of 1 minus t squared plus t, all divided by 1 minus t squared times the square root of 1 minus t squared. So then we can note that dt dx is equal to 1 divided by dx dt. That means we take the reciprocal of the expression that we just calculated. So this then gives us dt dx equals 1 minus t squared times the square root of 1 minus t squared, all divided by t minus 1 minus t squared times e to the t. Note here, e to the t is the reciprocal of e to the negative t. That is, e to the minus t is equal to 1 divided by e to the t, and e to the t is equal to 1 divided by e to the negative t. Now, we need to find our derivative with respect to t for y. So, y is equal to sine inverse of t. So, this means dy dt is equal to 1 divided by the square root of 1 minus t squared. This then gives us dy dx is equal to 1 divided by the square root of 1 minus t squared times 1 minus t squared times the square root of 1 minus t squared times e to the t, all divided by t squared plus t minus 1, which then allows for the square root of 1 minus t squared to cancel from both numerator and denominator, which leaves us with 1 minus t squared times e to the t divided by t squared plus t minus 1. And we have shown that which they asked us to prove. Moving to the last part of question number 1. We see that the last part asks us to show that f has no stationary value And we have to recall that stationary points exist when dy dx is equal to 0. Taking dy dx from our previous calculation, we see that we have dy dx equal e to the t times 1 minus t squared divided by t squared plus p minus 1 equals 0. This means e to the t times 1 minus t squared is equal to 0 because our denominator can be ignored here. And this then gives us 1 minus t squared is equal to 0 since e to the t can never be 0, which means that t squared is equal to 1, which then gives us t is equal to plus or minus 1. But the function is only valid for t inside the set of -1 to 0.5, not inclusive of -1, but inclusive of 0.5. So we realize that the function is not stationary over the given domain. This would be stationary only if we were given that -1 is a part of the domain. So therefore not stationary in the given domain. And that brings us to the end of question number 1. I'll see you guys over in part 2.
That is it for this video. Please remember to hit the notification bell, like, share, and subscribe for future post notification.